Hi students, in this week's video, we're going to do plane geometry. The questions are from assignment 18. In this chapter, plane geometry, there are a lot of things that we need to recap on, such as all the angle properties we've learned so far, the test for proving similar triangles, the test for proving congruent triangles, all the angle properties in the circle, and particularly there are two important theorems that is new in this chapter, and they are the midpoint theorem. So in the midpoint theorem, if you're given the triangle ABC, and if you're told that point D and E are midpoints of the sides AB and AC respectively, then we can safely say that DE is parallel to BC and DE is equals to half BC. So this is midpoint theorem. So this part that I've highlighted must be given. And the midpoint theorem can only be used on the triangle. That's why it says in triangle ABC. So if these are the information that's given to you, then you can safely use this. You can safely say that the line DE is parallel to BC and the length of DE is half times of BC. So this is midpoint theorem. The other theorems that we need to know very well is the alternate segment theorem. And this is what it means if you have a tangent line, AT. Tangent line is a line that touches the circumference at only one point. So in this case, it touches the circumference at point A. And if you have a triangle, you just make sure that this triangle, all the points A, P, B are touching the circumference of the circle. And this particular angle, BAT, is equals to APB. Or you can look at the other way around. It's the angle, the highlighted, okay, that call this Z. So ZAP is equals to ABP. And this theorem is called the alternate segment theorem or the tangent chord theorem. Right, I'm going to show you how we can actually recognize the angles using the alternate segment theorem. So first of all, to use this alternate segment theorem, we have to look out for tangent lines. Right, so a tangent line is a line that only touches the circumference at one point. That is the point of contact, let's call it A. And from that point of contact, we can draw a chord, another chord, and one more to form a triangle. All right, and you have to make sure that all these points must touch the circumference of the circle. That's very important. Right, so alternate segment theorem says that if this is the angle we're interested in, right, then so this angle, if you're going to use this chord to separate the circle, we actually have two segments. Right, this one, the one that it's called the major segment, and this is called the minor segment. So you can see that this chord that I've colored in red actually separate the circle into two segments. Right, so alternate segment means that the angle, the angle that's equal to this highlighted in purple, or sorry, in blue, must be in the alternate segment. That means must not happen in the major segment. It have to happen at the other segment. The other segment is this one that I've highlighted. Therefore, this angle must be here. Okay, so these two angles must be the same. So this is alternate segment theorem. Alright, so I'm going to show you using another example. So supposing I have a tangent line here. Okay, and then this is my point of contact. I can draw. Okay, wait, I don't think I'll use yellow. Let's use green color. Okay, so this is my point of contact. I draw three chords. Alright, so if I'm interested in this angle, then this angle will be equals to this one here. Okay, right. You see the two different segments. Let me highlight for you two different segments. The one in red and the one in blue. So the two angles must be in different segment. That's called alternate segment. All right, let me show you another one. Okay, supposing your tangent line is here. Right, then so this angle here will be the same as this one here. Okay, and this will be equals to this. Okay, right, let's look at the first question. So for the first question, you're given the quadrilateral. Quadrilateral is just a figure with four sides, not four-sided, four sides. A, B, C, D, and you are particularly told that PQR and S are midpoints of A, B, B, C, C, D, and D, A respectively. Right, so prove that PQRS is a parallelogram. Alright, so to prove something is a parallelogram, right, we can, these are all the properties of a parallelogram. So as long as it's satisfied, any one of these conditions means you have done the job of proving that the quad is a parallelogram. So for example, if you have proven that this particular quad has two pairs of parallel opposite sides, it has two pairs of equal opposite sides, it has two pairs of equal opposite angles, it has one pair of parallel and equal opposite sides, or if the diagonals bisect each other, then you can safely say that the quad that you are proving is a parallelogram. Okay, right. So let's look at what does PQRS as midpoint means. It means that we can actually use, yes, the midpoint theorem. Okay, but you have to be careful because the midpoint theorem can only be used in a triangle. So therefore, I need to bisect my quadrilateral ABCD into triangles. So how do we do it? Right, so let's look at triangle ABD first. So if we write triangle ABD, this is the one we're interested in. Okay, so you're given that all these are the midpoint, right? And if those are the midpoint given to you, remember what we can conclude? Yes, we can conclude that PS is parallel to BD. So that is in triangle ABD. Okay, let's look at triangle CBD. So in triangle CBD, right, so you're given these two as midpoint. So we can conclude that RQ is parallel to BD. So if you were to look at it, can you see that this is the connecting agent? So PS parallel to BD and BD is parallel to RQ. So we have PS parallel to BD and BD parallel to RQ. So what is the conclusion that we can say here? Yes, the conclusion we can say here is therefore PS is parallel to RQ. Okay, so we would have then PS parallel to RQ. So that is one pair. That's one pair of parallel opposite sides. So we need to find another pair. Okay, so to find another pair, we need to look out for one pair of, sorry, we need to look out for another two triangles. So let's look at ADC. So in ADC, you'll see that S and R are the midpoints. So therefore, SR is parallel to AC. Okay, and likewise in triangle ABC. So now let's look at ABC. Huh? ABC, where are you? Here. So you're given this P and Q are midpoint. So again, we can conclude that these two lines are parallel. So SR is parallel to AC and PQ parallel to AC. So AC is our connecting agent. So SR parallel to AC, AC parallel to PQ. So the conclusion we can have here then is my PQ is parallel to SR. Alright, so I actually have two pairs of opposite parallel sides. PS parallel to QR and PQ parallel to SR. Right, so therefore we can conclude that PQRS is a parallelogram because it has two pairs of parallel opposite sides. Right, let's look at the next question. So the next questions we're given is circle and summed in the tangent line. Right, a tangent to the circle at T meets PR at S. So this is my tangent line. And we're given PQ is equals to PR. PQ is equals to PR. So right, so what does it mean by saying PQ is equals to PR? It means that these two angles would be the same, right? And what are we supposed to find? We're supposed to show the angle TSR is 90 degrees. So we're supposed to prove that this guy here, okay, is 90. To prove that it's not 90 yet, we need to prove it. Alright, so how do we go about it? Okay, so let's see how we can actually make use of our tangent line. Okay, let's see how we can make use of a tangent line. So this is our tangent line. And from this tangent line, we can have one chord, another one, right? So that here we can use alternate segment theorem, right? Okay, that is one thing we can use. Another thing is that if you were to examine the diagram carefully, this is our diameter. This is the diameter because O is the center of the circle, so PQ is our diameter. So we can actually say this is 90 using angle in the semicircle equals to 90. So these are the two things we need to take note of. Okay, and of course, another one is what we mentioned just now. These two angles are the same. Okay, so let's go about solving it. So in triangle PQT, we're going to let the angle PQT be to be alpha. And then, yes, so using alternate segment theorem, okay, alternate segment theorem, right? This is one segment, right? So the other segment will be here. So that explains why angle PTS is alpha also. Okay, so I'm going to erase this. There's too much thing on the screen. It's very, very confusing. All right, and yes, so we need to write down the reason. So the reason is using alternate segment theorem, or you can use the other one. It's I can't remember the one is what something to do with the chord, but I prefer to use alternate segment theorem. Okay, so of course angle PRQ will also be alpha because what's the reason given? Is we're given the PQ equals to PR, so therefore triangle QPR is an isosceles triangle. Okay, so you need to mention this part here. Okay, that QPR is an isosceles triangle. All right. Okay, and like what I've explained earlier on just now, your PQ is the diameter, so QTP is 90 degrees, angle in the semicircle. All right. Okay, then what do we need to do next? Yes, we need to find STR. So STR will be 180 minus 90 minus alpha. Angle sum on the straight line. So this small little angle here is 90 minus alpha. Alright. And from there we can actually find TSR, right? Which is 180 minus bracket 90 minus alpha, close bracket minus alpha gives you 90 degrees. And this is exactly what we are supposed to show in part I. Okay, so let's look at part 2. So in part I, we managed to prove that TSR is equals to 90. Okay, so the reason is it's not given. It's not given to you, but you prove it. So you should say prove in part I. Okay, you should not use given. But using proof in part I is more relevant because you actually make the effort to do it in part I. So angle TSR is equal to 90 proof in part I. So we're going to use the property angle in the semicircle equals to 90. Okay, so this is what happened. You have a circle that passes through the point TSR, right? And we prove TSR is 90, right? So therefore your TR must be a diameter, right? Must be a diameter. So using the property angle in the semicircle equals to 90, TR must be the diameter. And if TR is the diameter, then the center will have to be the midpoint of TR. Okay, so this is how we explained in part 2. Okay, why the circle passing through the points SRT has its center at the midpoint of TR. All right, let's look at the next questions. It's quite interesting questions. You have a circle, and of course, you're given the tangent line again. So this tangent line is BC, and with the tangent line, I can have all these chords. Okay, so I can use alternate segment theorem. So for alternate segment theorem, look out for tangent line and look out for all the chords, right? Okay, so we're going to use triangle ABD. We're going to use angle BAD to be alpha. BAD to be alpha. So if angle BAD is alpha, then yes, angle DBC will be alpha also using alternate segment theorem. And we're going to let angle ABE be beta, a different angle. Okay, so angle EBD will also be beta. Why is that so? Because you're given this particular condition here. The condition is not so much here, just this part here. BE bisects the angle ABDE. So BE here is your angle bisector. It's an angle bisector that bisects ABD. So therefore your ABE is equals to EBD. So that explains that. Okay, both of them are beta because the line BE bisects the angle ABD. Alright, then what's the next thing we need to do? Yes, we're going to look at triangle ABC because we're going to find angle BCA. So angle ABC, okay, wait, I think I made a typo error here. This is not ABC. This is angle BCA or ACB. This one here, this should be your 180 minus 2 alpha minus 2 beta. Okay, so it's angle ACB. Okay, angle sum in the triangle. Always write down the reasons. Okay, so that, and then we're going to look at triangle BEC. And we're going to find angle BEC, which will be 180 minus what we found earlier on, ACB, minus alpha minus beta, and you get alpha plus beta. So what's the conclusion here? So the conclusion here is your angle BEC is alpha plus beta. BEC here we found to be alpha plus beta. And your CBE, okay, this angle here is also alpha plus beta. So therefore, triangle BC is an isosceles triangle. All right, the next question. So next questions, we're given two tangent lines instead of one. If you look at the diagram, there are two tangent lines, one tangent line and another one. And if you recall, if you have two tangent lines, there's a particular angle property that says that tangent from external point. If you have two tangent lines like that, that's the center, right? So this will be 90, tangent perpendicular to radius. And this will be equals to this, right? And these two angle will be the same, right? Okay, so this is tangent from external point. Okay, external point means if I'm going to label the chord, this is your external point. Alright, so we're supposed to prove that angle APB plus angle ADB is 180. So we need to go and find the angle APB, find the angle ADB. Add them together and show that it's equals to 180. Right, so the first step is let's look at triangle ABC. Okay, as usual, we're going to let angle BCA be alpha. You can call it any letter you want, call it X or Y or Z, whatever, but I prefer to use alpha. And then angle BAP will be alpha. Right, using alternate segment theorem. Okay, let me show you the triangle. So we are using this tangent line, this triangle. So my angle BCA is alpha. So here will be alpha also. Alright. And we're going to let an ABP is also alpha. ABP. Why is ABP is also alpha? Okay, why is that also alpha? If you were to look at the other triangle, the other tangent line here, and look at the same triangle that we are talking about. So can you see that this is also alpha? Right, so we also have alpha. Okay, so that is explain why that particular angle ABP is also alpha. Okay, because we have two tangent line there using the same triangle, two different tangent line. So it's a bit challenging or confusing, whatever you call it, but don't worry, just look at one triangle, one tangent line at a time, then you'll be able to see that. Alright, so angle CBD will be equals to alpha. Why? Because you're given this triangle to be isosceles, right? See the two lines here? So angle CBD is also alpha. Okay, given CD is equals to BD. So your CDB is an isosceles triangle. So CDB you can find will be 180 minus 2 alpha, right? Because this one will also, this will be alpha. Okay, right. So then finding CDB is to help us to find ADB. Remember, we need to find this angle ADB. So using CDB, I can use 180 minus that. Yeah, okay, angle sum in the triangle. Always write down reasons for whatever we've done. So angle ADB will be 180 minus bracket 180 minus 2 alpha gives you 2 alpha, and the reason will be angle sum on the straight line. Okay, so we are done finding ADB. Now we need to find APB instead. APB. So APB will be again 180 minus 2 alpha, angle sum in the triangle. Right. So when you add these two angles up together, you see that you get 180 minus 2 alpha plus alpha give 180 degrees, which is what you're supposed to prove in part I. Okay, so this is what we have in part I. Okay, all the alphas, they are all having the same angle. So we need to prove that APBB, given the APBD lies on the circle. Okay, so there are points on the circumference of the circle. We need to prove that PD this one here, that's parallel to BC. Right, so to prove they're parallel, we can use alternate angle. No, sorry, not alternate angle. We can use, alternate angle. Alternate angle or corresponding angle. So here, I think using alternate angle will be more relevant. Why? So in part 2, we already proved that PDB is equals to alpha, right? Angle in the same segment. Oh no, sorry. We didn't prove that. Okay, we proved that PAB, we let PAB be alpha. So if you were to concentrate on this circle, let me erase this one. We're going to concentrate on this circle. You see that, I think I'm not very good at drawing. You see that this particular, can you see these two angles are angle in the same segment? Angle in the same segment. If you have a chord, right? Okay, these two angles are the same. That's called angle in the same segment. Because you're coming from the same segment here, right? So therefore, PDB is equals to alpha using angle in the same segment. And if that is the case, what is the conclusion? Yes, the conclusion is your PDB is equals to DBC equals to alpha. So therefore, using alternate angle property, your PD is parallel to BC. Alright, so that's how we prove it. Right, so let's look at these questions here. So in these questions, we have two circles, C1 and C2. C1, it's the bigger circle. C2 is a smaller one, and they intersect at 2 points P and Q. So the tangent to C1 at P meets C2 at R, and the tangent to C2 at P meets C1 at S. Okay, not to worry. All we are saying is that if you look at the diagram, we have this circle with a bigger radius, and this is our tangent line. Okay, so if you look at the smaller circle, so the tangent line is longer. Right, this is all they're saying. So we're supposed to prove that triangle PQR and SQP are similar. Okay, so we're supposed to prove these two triangles are similar. Okay, so right, so since we have tangent lines, then we should relate it to alternate segment theorem. Okay, so let's look at triangle PSQ first. So if you look at the triangle PSQ, then the tangent line that we are referring to will be this one. PR will be a tangent line. So if you're going to let the angle PSQ be alpha, then QPR will also be alpha using alternate segment theorem. Okay, right. So we are done with this. Then the next thing is that let's look at triangle PQR. So now we concentrate on this triangle. So if you were to concentrate on this triangle, then this triangle is inside this circle, right? So the tangent line will be SP. So when you're faced with this kind of problem, not to worry, we do one things at a time, one circle, one tangent at a time. So in triangle PQR, we're going to let angle PRQ be beta. And so therefore your SPQ will also be beta using alternate segment theorem. So you see that we have two corresponding angles the same. So now we can conclude that triangle PQR and SQP are similar because they have the same corresponding angle. Because if the two corresponding angles are the same, then the third one will be the same as well, right? So we just need to find two, and then we can conclude that they're similar and conclude it with a proof statement, such as they have the same corresponding angles. So that's part I. Right, so for part 2, since we've proved that PQR and SQP are similar, in part I we've already proved that, right? So we can use the ratio of corresponding sides. So using ratio of corresponding sides is quite easy. If you have already arranged that PQR and SQP, if you arrange it such that the P correspond to S, Q correspond to Q, and R correspond to P, then when you want to compare ratio of the corresponding sides, it's very easy. You just need to look, if you're comparing PQ, then that is, if you're using PQ, not comparing, if you're using PQ, that will correspond to SQ. So that's how we have it here, PQ over SQ. Okay, and if you're going to use QR, so your QR correspond to QP. So that's what I have here. Okay, so that's how you do it. So it's relatively easy. So the next thing is that I'm going to just do a cross multiply. So QP is the same as PQ, right? So you have PQ times PQ, so that gives you QP squared or PQ squared, but you write it as QP because we always answer to the question that's asked. So in the questions you actually use a simple QP. So QP times QP will give you QP squared, and then SQ is the same as QS. So QS times QR will give you bracket QP cross bracket squared. So that proof part 2. Okay. Right, so in part 3, you're given points A and B lie in the circumference of C1 and C2 respectively. Points A and B lies on the circumference of C1 and C2 respectively. So we ask to prove angle SAP is equals to angle PBR. So the one highlighted for you in yellow, we need to prove that two angles are the same. All right, so if you look at this circle here, concentrate on this circle. You'll see that I have a cyclic chord here, a cyclic chord. A chord is the one with 4 sides. Cyclic means it's inside a circle. All these 4 points must touch the circumference of the circle. So that is a cyclic chord. So for cyclic chord, what angle properties can you think of? Yes, angle in opposite segment. So SQP, so I can actually find SQP by taking 180 minus alpha minus beta. So where is my alpha, where is my beta? So if you're using this triangle, SQP, we have to use this triangle first. Okay, to find SQP, to find this one here. So that will be 180 minus alpha minus beta. So that's angle sum in the triangle. And then with that, I can use angle in opposite segment to find SAP. Okay, right. So I settle with SAP. So you can do the same for the smaller triangle. Do the same for the smaller triangle. We're going to find this angle first. Okay, PQR, which is 180 minus alpha minus beta, angle sum in the triangle, and then use the cyclic chord. Okay, to get alpha plus beta as well. So now we can conclude that angle SAP is equals to PBR equals to alpha plus beta. Right, so we come to the last questions. The last question is a very recent year question. It's in 2023, paper 2, question 3. So you're given a circle and a tangent line and also FD being the diameter. So if you're told that FD is the diameter, what's the concept that you can think of? Yes. Okay, your angle FBD will be 90 degrees. What angle property is that? Correct, it's angle in the semicircle. Okay, and we're also given tangent line. So ABE is a tangent line. So with tangent line, what concepts can we use here? Yes, we can use alternate segment theorem. Okay, so with alternate segment theorem, right, so let's look at this triangle here. If you're interested in this angle, the chord that's opposite this angle is BF. So BF will separate your circle into 2 segments, right? The one highlighted in blue and the little one here in yellow. Okay, so for alternate segment theorem means the angle must be in different segment. So if this is the angle that you're interested in, then it's equals to this angle here. All right, so we need to prove that the 2 triangles, the one highlighted in blue and the one highlighted in yellow, are similar. Okay, so let's use alternate segment theorem first. As what I've explained earlier on, we're going to let the angle be alpha, and so therefore ABF will also be alpha using alternate segment theorem. Okay, then the second thing is that you will see the angle ADB is equals to ABF. Why is that so? Correct, that is the angle that can be found in both the triangle, can be found in triangle ABD, also found in AFB. So therefore, it's called the common angle. And since we have both triangles having the same corresponding angles, then we can say that they're similar to each other. Using corresponding angles are the same. Oh, okay, that's not very grammatically. Can we just say that triangle ABD is similar to triangle AFB since they have the same corresponding angles? Okay. Using corresponding angles as the same property. Okay, let's add in the word property. Okay, so triangle ABD is similar to triangle AFB using corresponding angles as the same property. Okay, that's done for part A. Right, so for part B, we're asked to explain what kind of quadrilateral is EBFC. EBFC. Oh, that's one here. What sort of quadrilateral? Is it a parallelogram? Does it look like a parallelogram? Definitely not, right? Does it look like a triangle, a rectangle, a square? I think it looks more like a trapezium. So if it looks more like a trapezium, then what are the properties of a trapezium? What do we need to prove, that to show that it's a trapezium? Yes, so if we were to recall, a trapezium have only one pair of opposite parallel sides. One pair of opposite parallel sides. So if we can prove that, then we can then we can say that this quad is a trapezium. All right. So the first thing, what do we need to do? Okay, we draw a line from B to C. Yes, we need to find to show that the one highlighted in yellow, it's a trapezium. Okay, so BXC is 90 degrees because you're given BC as a diameter. See? So BC as a diameter, so BXC will be 90. What's the reason? Correct. Angle in the semicircle. Okay. The angle DBF is 90. Okay, why is DBF 90? Okay, as what I mentioned earlier on, you're given FD as the diameter of your big circle, right? The big circle here we're talking about. And FD is the diameter. So therefore, this is 90 using angle in the semicircle. Okay, right. So if we have the two angles equal to each other, then what property can we use? What can we say about BF and EC? You see, you have 90 and 90. So 90 and 90 add up to be how much? Add up to be 180, right? So what angle property can we use here? Yes, we can use interior angle property. And if we are using interior angle property, then your BF must be parallel to XC, right? And if BF is parallel to XC, then we have actually your EXC is a straight line. So XC, that means BF parallel to XC means that, okay, we need to include one more part here. BF parallel to EC means BF is parallel to EC. Okay, include that. Right. So if BF is parallel to EC, then we have shown one pair of opposite parallel lines. So therefore EBFC is a trapezium. Okay, so that ends the whole video. So happy learning.